Okay, welcome to the fifth of these tiny lectures. And now we come to our first formulation, which is diffusion. Now, very simply, I would like to start off with just imagine two walls. And across these two walls, just imagine that uh, particles come like this and they go out like that. So let's say that the first wall is, and we're just talking about a 1D space, so I'm just talking about the x coordinate over here. So let's say that this is x and this is x plus delta x. Now let's say that the current coming in here is Jx, the current going out here is Jx plus delta x. Let's say that there is some little absorption going on over here. So absorption, and let's say that there is a source. So let's look very simply at this picture. And so let me just put in some numbers. Imagine that three particles are coming in, five are being produced, two are being absorbed, and how many would go out of here? 3 plus 5, 8 minus 2, now 6 would go out. So basically the balance equation would be 3 plus 5 is equal to 2 plus 6. Now this is called a conservation equation. It conserves the number of neutrons entering and leaving. So this is a current. Current means n, the number density, multiplied by the vector v. So current has units of numbers per cubic centimeter of neutrons multiplied by speed. So it's number per centimeter square per second in a certain direction, and in this case in that direction. So basically what can I write? I can write down that Jx, because it's a per centimeter square, so I can multiply it by the perpendicular area that is crossing. So this plus the source, let's say it's a volumetric source, so let me multiply it by the volume of this box, imaginary box like that. So this is a box, distance delta x, delta y, height delta z. So the balance equation is Jx A perp plus S delta V is how many are going out? Jx plus delta x, same perp, plus this minus the number of absorptions. Now if I write the number of absorptions like this, that it's the macroscopic cross-section, macroscopic absorption cross-section times the flux. So flux is the same units, neutrons per centimeter square per second, multiplied by the volume. So this becomes the balance equation. Now what I'm going to do is, so if you just look at it like this, Jx, what's the perpendicular area? It's delta y, delta z, plus S, what's delta v? It's delta x, delta y, delta z, is equal to minus sigma A phi delta x delta y delta z is Jx plus delta x delta y delta z. So let me cancel these things over here, and what I get is that if I take this j on that side, so I get Jx plus delta x minus Jx, and let's divide by the delta x. So divide by delta x is S minus sigma A phi. Good. Okay, now let me use Taylor series over here for x plus delta x, and let me just use Taylor series to the first order. So in other words, I'll ignore terms of second order. So Jx plus delta x is Jx plus dj by dx times delta x. Okay, and let me put this over here, that it's not equals, it's approximately equal to first order. Now these two cancel out, and what you see over here, you see the diffusion equation which comes out of this, and the diffusion equation over here is dj by dx plus sigma A phi minus S is equal to 0, right? Okay, now we've got two variables, j and phi, and we've got one equation. So we've got a current, we've got a flux, so we cannot solve it. So here, let me call this equation 1. And now let's look at Fick's law. Now Fick, and sometimes also called Fourier's law. So Fick said there's a relationship between cause and effect. If two walls are at different temperatures, then what's going to happen? Heat is going to flow. Because nature will not let a hot wall and a cold wall remain hot and cold. They will have to come to some equilibrium temperature by exchanging heat. So the relationship between cause and effect is this kind of a relationship, that J is equal to minus D, some diffusion coefficient, grad phi. So vector gradient, vector current, scalar flux. Cause, effect. Cause is the flux, effect is the current. So let's call this equation 2. Now let me put this in here, and what do I get? I get d by dx minus d, and in this case it's slab geometry, so d phi by dx plus sigma a phi minus s is equal to 0. So let's take the thing and on the right hand side, and let's assume that d is not a function of position. So then I can take it over there and I can say d2 phi dx squared minus sigma a phi plus s is equal to 0, and this is called our diffusion equation. So, diffusion equation in its simplest form. Now, what's assumed over here? That all the neutrons have the same speed, which you know is not true. So, it's a very crude model, and it's called the one group model. Now, one group model, is it good, is it bad? I can tell you it's not very good, but it's a starting point. So, in the next lecture, number 6, I'm going to write a two group model. So, once we do that, then I'm going to teach you how we can solve the diffusion equation for the flux. What are you trying to get? The flux. You're given the material, you're given the source. Now in this case, I've assumed there's no fission over here. So in the next lecture, I'm going to put a fission source over here, which means neutrons being born out of fission taking place. Thank you.